Full screen here. All right, coming up to the end of the semester. And I see we got some reflections on the board. I'll try to deal with that as we go along. So yeah, in this video, I'm hoping that we can strengthen or deepen conceptual awareness. I'm going to talk about some graphing principles, polynomial tugs of war, rates of change. We're going to build up from the linear to the quadratic to the cubic, and hopefully add a little understanding to what we've been talking about all semester. All right, so there's 4 ways to graph the equation of a line. You get drilled in Algebra 1, mx plus b. I personally prefer this form, which is not a technical graphing form shown in the textbooks. It's very similar to the point slope form. It's just moving the constant on the left over to the right. So 8x plus 3, I don't think we're showing anything different here than what's in the textbooks. A 0 gets you 3, and you're going up at 8 to 1. All right, so should know that. If you put a 0 in, you get 8 times 0 is 0 plus 3, 0 plus 3. If you put 0.001 in, you get 0.008 plus 3. And I hope we can see that's still going up at 8 to 1. All right, we'll come back to this as we build our understanding of quadratics and cubics. This is very helpful for some aspect of graphing that we'll discuss in just a couple of minutes. All right, so I need an eraser. I got one. So if we were going to graph y minus 5 equals 2/7 x minus 4, you're supposed to see 4, 5 satisfies the equation. We'll put a little dot there. And you're going up 2 and over 7. And you should know how to do that from Algebra 1 and Algebra 2 practice. And if you go up 2, then we have a new location of over 7, 11, over 7, up 2, 7, 11, 7. Doesn't hurt to show that. And then you got your standard form. Standard form, you're using zeros because zeros, 7 times y is a product. If you make it 0, it's gone. And you can see your x is what, 14? 30, yeah, 14. So if x was 0, y is -6. And I think I said 14, 0. Connect those dots and you got that graph. And this is exactly the same as point slope. It's just easier to read. I'm at location 7, 3. And I'm going up 5 and over 2. And I have a feeling for that. So nothing new there. All right. So let's look at y equals 8x plus 3. But we're going to look at quadratics now. And to make a quadratic, I obviously have to add a quadratic term. Okay, let's establish some things that we've looked at. Quadratics, 4-sided figures, and the square is a special case quadratic, where all the sides are the same. Then we started talking about rates of change here, and we'll talk about that some more in this example. But let's start off with what would happen if I added a quadratic term. Well, let's actually do some 0 work here. Let's add the quadratic term here. And if I put a 0 in for x, I get 0 plus 0 plus 3. So nothing's changed. I'm at 3. I guess I've shown it here. I'm at 3, but I'll show it here in both places. And what happens if I go 0.001? Well, that doesn't change this, but does change this one. 0.00001. And, you know, the term that's becoming very familiar lately is influencers. And I think you can think about each of these terms as influencing movement from an altitude of 3. Look like they're both pulling up. Who's pulling harder locally? Who's working harder here? The linear term. Yeah, because this is almost like exponential decay. The more 0.001, the more zeros I put in there, the smaller it's getting, not bigger, right? 1/10 times 1/10 is 1 over 100. That number's smaller than the one I started with. Okay, so that's important to know. So I guess if I'm adding a little bit, we'll go over here now, and if I put a 1 in, I get 1 unit plus 8 units plus 3 units. There's my 11, but I'm a little bit higher. So instead of 11, I'm at 12. And it looks to me like I'm not on that line anymore, and I'm getting a little bit of a bend. Yes, I am. And I hope that we realize we have a cup shape up. And it still looks like I'm going up at 8-1 right there, and I am. I'm still going up at 8-1. So we have actually an embedded tangent line in this graphing form. And what have we done? We've taken x squared plus 8x and reshaped it into a square. And that's x squared plus 8x plus 16. This doesn't have the plus 16, so we do minus 16, and we basically put this in graphing form. And we aren't doing the drawings forever. No, we're cutting to the chase, and we're saying minus b over 2a is evening off the sides of a rectangle. Ax squared plus bx is x times ax plus b. And there's our minus b over a. That gets rid of the width. And there's our 0. And what's between 0 plus minus b over a? What's the number between those? Divide by 2, and that's your shortcut to find the x value. And then you plug in minus b over 2a into the equation to find the y. And that's not hard. Minus 8 over 4, negative 2. And if you put negative 2 in, negative 16 minus 8 plus 3, you get minus 5. And I know the slope here is 0. Now, how do I know the slope there is 0? Well, we got to go back to look at how things change, right? And if I did a 3 by 3, I get 9 units of area. But if I add a little strip, then I get that little strip has width of 0.001, then my area from 9 goes to 9.006001. And I can see that I've got a twice the x value. We've talked about that. It's an emerging understanding, and half a dozen of you in class, it clicked for it today, which is nice. You can talk to your classmates, and we got another week and a half to bring them along. All right, so what did you do in class today? You looked at the derivative, which is 2x plus 8. When does that equal 0? 2x, yeah, 2x plus 8 equals 0 at negative 4, which means I botched this number. How did I botch that number? Minus b over 2a, 2 times 1, minus b over 2a. Yeah, 8 divided by 2 isn't 2. All right, so I'm not going to do the video again. I'm here. I'm sure you caught that. And have a good laugh. All right, so that slope is 0, and this seems to give me the slopes that I'm looking for, because if I put a 0 in here, I'm going up at 8-1 when I put a 0 in here. And when I put a negative 4 in here, I got a slope of 0. All right, so we've been looking at that a little bit. And so when would we be, if we look at it from a geometric standpoint, and the layering, the bigger squares get more area accumulated. And the one that gets the least amount of area accumulation is when the square doesn't exist. There's no area. If there's no area, there's no side lengths. And the side lengths determine the rate of area accumulation. I'd like you to hear that before you get to a calculus class. Because I think the secret to understanding that level of study is connecting it to geometry. All right, because that's where it came from. All right. So, keeping that in mind, let's go over and summarize some things we've done. And now I'm on the zeros and ones video. The zeros and ones, because that's how we really can graph things quickly for polynomials, is understanding that those are the easiest multipliers, 0 and 1. So this one here, x minus 2 plus 7, right? And that's linear change, something to the first power. which means our change in x is going to come from linear change. And what was our linear change? From 2 to 5, just 3 units. When I put a 5 in, this entire calculation changes by 3. And 7 to 15, we're going up 8. And so there's a quick way to write the equation of a line. Some students are still writing it from mx plus b form because it got drilled. Doesn't mean it's the easiest. Okay, so we move to the quadratic. All right, and we got an ax squared plus bx plus c, but we're still measuring from 2, 7. So there's an awful lot of similarity in how we start. Because I want to talk about change. But change here is not the same as change here. Change here is quadratic change. When I drop a 5 in, there's the change. And that change in x, 5 minus 2 is still there, but squaring changes those numbers completely. And that's what we studied this semester. Now it's time to talk about it in general. But I'm still going from 7 to 15, I'm still going up. But what's my square change from 2 to 5? That's 9 units. And that is that equation. Now I just switched the x's and the y's because I'm really changing squaring. I'm inverting squaring to square rooting. And so start very similarly. But this is square root change. So I've got to cancel square root change. But change in x is 8, but this is square root of 8 change. I have to cancel that in order to bring 2 to 5, which is 3 units. Now over here, the squaring was with the x's. Not squaring that anymore. And I switched the x's and the y's. Now it's 7, now it's 2. In other words, I hope you can see that addition of 7 becomes subtraction, squaring in the denominator becomes square rooting in the denominator, so on and so forth. Somewhere in here, I know this is an ugly board at the moment, and it's a little disorganized, but hopefully you're following. So what do we got over here? We've got 8x plus 3, so we still have that, 8x plus 3. And what's a minus sign going to do? Well, minus sign is going to make it, when I add 1, it's really taking away 1 from 8 units of change. And I get that bend. And we know that bend is eventually going to go down. Well, how about this one? It seems like this just got a little stronger, this term, a little more forceful. Don't think it's going to take as long. Okay, and we put those in graphing form. We've looked at those. But there's an interplay here. All right, and we look at that interplay, 2x squared minus 20x plus 7. We do that, minus 20x plus 7 is on this side going down. 20 divided by 4 is 5, so on and so forth. We manipulate it, and we're getting pretty good at that. What happens if I throw a cubic term in there? Still got 8x plus 3. 0, 3. I'm still going 8 to 1 there. This term is most powerful at 0. As I move from 0.001, this became more important. And as I continue to move to the right, this is going to have an influence on that change. And then eventually this is going to have the biggest influence. So hopefully we can kind of see that taking shape. All right. We've got our, and I don't know yet if that's really going to change until I do more analysis. And where's the analysis going to come from? And I'll come back to this. It only takes 20 seconds to put that in graphing form. All right. It comes from completing the cube. In other words, x times x minus 2 times x minus 10. You saw that factoring, I'm sure, in your class, 0, 2, and 10. But there's the point of inflection. And it turns out it's minus b over 3a. It's the average of the roots. Why? Because I'm going to average the 0, the 2, and the 10. It's like putty. These are already the same, x, that's the same. I'm trying to make a perfect cube. Because what happens when we put something in graphing form, and we did over here, I'll put it in graphing form, the one I just did for you here. If I put this in graphing form, it's 2x minus 5 squared. Let's see, that's 50. So minus 50 plus 7 minus 43. That's graphing form. Well, I see two terms instead of three. So I only have the quadratic working on the constant term here. It's easier to visualize. Of course, it's better if I put Rene Descartes in a better position to visualize. I'm sorry, Rene. I had you at an angle. That moves into trigonometry. We're not going there right now. All right, so let's go back here. Now, I could put this one in graphing form, but I got something that works nicely over here, so we'll play with it. All right, so I hope you can see if you put 0.001 in, that's got 9 decimal places. That's got 6 decimal places. That still has 3. This is still Mike Tyson in the ring, in his prime. Yeah. But as we move away from 0, each of these starts contributing more and more. For instance, when we put a 1 in, 1 cubed, I'm going up 1. 1 squared, I'm going down 6. I'm going up 8, and I'm still at 3. Now, I didn't move that much, and look at how much more important that number seems to be. And that if I go to 10, 10 cubes 1,000, minus 600, plus 80, plus 3, more dominant roles over here, but Mr. Big. And that's why this is end behavior. It's the end of the graph, the behavior going up. All right, so it bends here. That's the point of inflection. How hard is it to find? The average of the roots from completing the cube. And if you want to see that process done, go to the playlist and look at one of the completing the cubes, or if you want to put cubits in graphing form, in a more, if you want a deeper conversation, go look at that. Right? But it's not hard to get minus b over 3a. It was hard for me to get it minus b over 2a over there. I made a careless error. So I'll be more careful here. 6, this is a 1. 3 times 1 is 3. I now know that happens pretty quickly at x equals 2. Pretty quickly. And if I put 2 into the equation, I get a nice influencers, yeah. I get a nice round number, 8. And I know the next one is 3 times that in opposite because of the geometry of the, I should put all the cubes here, talk about how it's changing. I will talk about how it's changing right now. Here's a perfect cube. All the sides are the same. And if I put more volume on it, I've affected the surface area and more volume. And that's the rate at which it's changing. So what's standardized? The height. This has a little bit of height. Think of it as the 0.001. And then you've got 3 squares. So if I was to cube 3, I'd get 27. And if I were to cube 3.001, I get 27.02. Let me make sure I got this right. 3 squared, 3x squared. Yeah, 27.009001. Took me a minute, right? And that's going up at 27 to 1. And if this is a 3 by 3 by 3, now 3 times 3 is 9. So I got square area of 9, a little bit of thickness gives it volume. And I got how many of those squares? 3 of them. And that's really the rate of change of the cubic is 3x squared. So at 2, I'm going up at 3 times 2 squared, 12 to 1. At 3, I'm going up at 27 to 1. At 4, I'm going up at 48 to 1. And at 0, I'm not going up at all. Why? There's no surface area to a cube of 0 times 0 times 0. Okay, so it's linked to geometry, and that's what you'll study in more depth, but it's happening in a year and a half. And I think it's very important to get these concepts started. thinking about it, just start. All right, so I put a 2 in, 8, that's going to be 3 times that, but the opposite. So minus 24 plus 16 plus 3. Hope I didn't make any careless errors late in the day and I'm tired. Minus 16, all you have to do is double that and change the sign for a shortcut. That cancels with that. And so I guess I'm at 3. Whoa, whoa, I like that. I like that. It was there. I got a better sense of what things look like, and that could be fun. This could be a lot of fun here. 2 gets me 3, which means that over here, 4 should get me 3, and I actually have a factored situation here? No way. There's no way. Oh, I'm having fun now. Let's keep going. All right, maybe it's late in the day. I could have done something really stupid. Hope not. Let's find the rate of change here. So C minus 3AH squared. C 8 minus 3 times 1 times 2 squared. I think I'm looking at 8 minus 12 minus 4. So my slope here is minus 4. Wow. Huh. Wow. All right, well, let's just play with it. So now I got the graphing form. I hope I didn't make a mistake. I'll check it later. So 2, 3. So x minus 2 cubed and x minus 2. I got a linear component here. Why do I have a linear component? Because at 2, 3, cubic would look like that. If all I graphed here was 2 comma 3, then x minus 2 cubed plus 3 is not changing at 2 much at all. Why? There's no box. 2 minus 2 cubed. No volume. No changing square area. But this is going down, which means it's got a linear component, and that linear component is minus 4x minus 2. And I know when I put a 2 in, I want a 3. Wow. Interesting. Huh. And I know that, oh God, I hope this is right. All right, I know that those slopes are 0. And I know that the x value here can be measured from 2. Because it's all about the interplay of the slopes. And in this case, I feel like I'm almost diving into calculus now because I think you're ready for the conversation. But I'm going backwards from 2 to get to this x value, and it's going to be the opposite of going down 4. It's going up 4, and 3 times a is 3, and that's that x value. And that is a little bit near 1, and 2 minus 1 is near 1, but it's off-centered a little bit, more in that direction. And then this one would be x equals 2 plus the square root of 4/3. And all of this is explained in putting cubics and graphing form. All right, but what's the difference between this line of work and that line of work? 3 terms instead of 4. And you can keep doing that through x to the 4th, x to the 5th, x to the 6th, x to the 7th. They're all graphing forms. They just get rid of the second term, all right, by completing the quadratic. I don't know how to draw that, but you can extrapolate it. Now, what am I missing here in terms of conversation? That's still the tangent to the y-intercept. Okay, and now hopefully you see the interplay of these. And this takes over that pretty quickly. Pretty quickly, this will overtake that in terms of turning it back in the other direction, because the rates coming from this term will exceed the rates coming from this term. As in terms of influencing. I don't like the way I said that, so I retract what I just said. It sounded awkward, but that's why I like repeating things, because the next time I talk about it, maybe say it a little better. All right. The actual, I want to check this. I'm going to use calculus to check this right now, because I like that, and that means that I could lower this by 3 units and I'd have a graphing form, right? So what I'm thinking about right now is just moving this graph down 3. And if I move it down 3, I get 0, 2, and 4. So I get x times x minus 2 times x minus 4 plus 3. I'd like to multiply that out and see if I get this. Oh, can I do that real quick? Minus 2 times minus, so minus 2x minus 4x. Well, that adds up to minus 6, yep. times x squared seems to be something interesting. All right, so what did I say the graphing form was? Where am I in my conversation? I was gonna do something. Oh, yeah, calculus. So y prime, 3x squared, there's the 3, that's the how that changes. Minus 12x, that's what a lot of students learn in class today, plus 8, and that's a quadratic. And it has a minimum here. A minimum. And what's that minimum? That's the fastest I'm going down right there. All right, and that comes from minus b over 2a, which should be 2. So minus b, 12 over 6, that's 2. And if I plug a 2 in, I should get a slope of 0. No, I should get a slope of -4. So this is minus 12, minus 24 plus 8. So something is minus 12 plus 8. Yes, I do. So that verifies that. So the calculus sounds good. And if I were to take that derivative, I would get, so where the heck am I? I'm here. I'd get 6x minus 12. And when does that equal 0? That x equals 2. 6x minus 12 goes from negative to positive at 2. And so I have negative acceleration. That's why it's concave down. And then positive acceleration. So it seems to be matching up nicely. And if I didn't make a real bad math error, I think everything I've said is true about these functions, but I might have made a math error there late in the day, and I certainly end up getting careless. Minus b over 2a. I didn't double the 2 times 1. Yeah. Whatever I did, it was wrong. I divided 8 by 2 and said 2. Not smart. All right, so let me sit down, upload this, and put it out there. Yeah, there's stuff to think about. And you got to start conversations. And you got to keep having them. And you got to keep working with the material. Otherwise, you learn something for a test. 6 months later, you don't remember it. And that's what I was seeing with students coming into the classroom. Weren't able to use the foundational Algebra 1, Algebra 2, and pre-calculus topics. They came at them all different directions. And, sine of 2 pi over 3, students were saying, oh, we just memorized that. Not good enough. Not good enough. So a little bit of everything a day, often, get out there and play around with this stuff and do the lesson sets and do yourself a favor and make it working knowledge. Okay, there's my ramble. Have a good one.